Anyone from quality assurance also? Sorry. Okay, so that's the profile roughly fits what I planned for today. So that one. So let me just give you an initial overview of what I had in mind for this. Right? One is that we have. I'll just give an initial bit of motivation around this part and what we intended it for. I've already done a little bit of that, but I'll just do that anyway. Then what I do is I use a small problem as a kind of a context for today's discussion. It's a very easy to relate to topic. I think everybody will be able to relate to it. That's my hope, at least. And it's got a little bit of a historic twist to it too, so which I kind of enjoy. And then what I'll do is it's basically just guessing gender by giving somebody's name. And it's kind of a fun problem to pick for starters. So what we'll do is we will dive straight away into testing what we talk about there. Delete this clicker. So and then we'll also look at how to actually print this stuff. Given that its simplicity, I think my purpose behind this is to sort of illustrate all the different phases that typical machine learning projects go through. And how even if you don't necessarily come from or are directly participating in such a project, it is actually possible for you to grasp some of these principles and dive into and have a conversation around what sorts of problems that you can contribute, both in terms of existing projects as well as if you're looking at if you're working on a particular product and you may come across a particular hey, this should be solvable using machine learning. So there are more and more of those kinds of problems coming up in the context of today's work, and that's the hope behind the purpose of this stuff. So we'll also look at yes, as we progress through this, we'll be diving a little bit deeper and deeper and deeper. We'll be digging deeper, but hopefully I go slowly enough that it'll be easy to follow. That's my intention behind this. And finally, I'll finish off with something that's pretty much at the bleeding edge of today's work, but it's a very gentle introduction to that bleeding edge again. So one thing that I'll do is I'll focus heavily on that part of it, testing. So because that's the crux of all the machine learning work that we have seen up to this point. And almost there is a bit of a misconception around the general field of ML and AI, at least in the communities that I see here, that it's all about algorithms and math. That's a very small part of the general endeavor. I mean, if you typically go to a Kaggle competition and you look at how many are familiar with Kaggle? Kaggle. So for those not familiar, Kaggle is an online platform where you can go and people post machine learning problems as competition, and you can go and try to solve them and win prize money. So for certain kinds of problems, the prize money goes all the way up to $30,000, etc. I mean, it looks like a fairly large prize money. You go and dig a little bit deeper into those projects, what you actually find is that the amount of effort that's gone into putting together that data set that they're giving you for that competition is probably 10 times as much, as expensive as the prize money that they're giving you. So typically, some of these data sets have costed over $500,000 to put together before it reaches the competition stage. So that's part of the reason why I'll be focusing on that testing part and how critical thinking is very valuable in that testing part, and it's something that it's very important for everyone to come to terms with. So that's the motivating bit behind it. So machine learning is eating software. I mean, the catchphrase is that software is eating the world, but in some sense, like there's a lot of buzz around ML and AI as it is normally known these days. I don't like to use that phrase so much because we're not there yet. So, as I said before, folks not from the particular domain also, it's important for them to participate in this conversation. And just as I mentioned now, critical thinking is an important thing that we bring to the table here. And I mean, in some sense, I think quality assurance people are far better placed to deal with this topic than most developers that I see at this point, because of the kind of mindset that you're coming from and the kind of when you're looking into all sorts of details about various things that developers not normally pay attention to. I'll come to some of those aspects. And this is the other one that I mentioned, that it's useful for you to be able to discover potential applications of the products that you're working on. So that's it. So this one for MLF experts, and so that's the goal. So if I'm going beyond this particular mandate at any particular point, please don't hesitate to stop me, ask questions. All of that's perfectly fine. So this is, I want to start with a kind of a personal anecdote here. It's just a really long time ago. It's practically 30 years ago. I was 13 years old. I think around that time, if memory serves. And a cousin of mine showed me, it was around the time computers were sort of getting visible. It was, I think, late 80s. My cousin just showed me this program on this blinking CRT monitor, which did this. It prompted me to enter your name. I just typed in my name, Kumar, which is what I'm known by. I said, hello, Mr. Kumar. And like, how did it know I was a guy? And then, like, this is my wife's name, but I just added it in. But then I tried to make a girl's name, but then it just put this properly. And so I was really fascinated with this. I was very young back then, and it's not, and it could just go on. I mean, you can just type in as many names as you wanted to, just put the appropriate prefix. And he challenged me to come up with like to guess what he had done in order to do that. And I'm like, did you put in all the names that you know of into the program? So because I don't know like how big that program would be. So we had all that kind of a conversation back then. So this is the context. Okay, so this is what we'll be diving into today. It's actually pretty fun. So so guessing one's gender, right? So one thing that I'll be doing in the course of this particular talk is I'll be using a particular kind of notation for the functions that I'm going to be describing here. So this is based on the language Haskell, which is like anyone familiar with functional programming in general. In any language is fine. It's not necessarily Haskell or anything. So JavaScript, Scala, even Java. I mean, if you're familiar with lambdas, that counts. Yeah. So that's good. So I mean, the notation is actually extremely simple. I mean, I'm not going to really write Haskell programs and show you and like dive deep in. That's not what I'm going to do. But what I'm mostly going to do is to just use the type notation of Haskell to express ideas, because I think it's an extremely powerful tool that very succinctly and precisely captures what we want to convey. So in this case, what this is basically telling you is that what the core function that was there in the slide before, the thing that took the name in and guessed the gender, that just basically takes one string argument and produces a gender as its output. It's one function that does. That's all the statement says. It's actually a very straightforward statement. And what's the gender? It's either male or female. Okay. So this is the moment we start declaring this as a model of what we want to build here, it already starts getting interesting. Whether this model is actually complete enough, is this adequate for the problems that they're looking at? What if somebody doesn't want to get addressed as Mr. or Miss? What do you do? So it already starts getting into that kind of an interesting territory. So we are extreme TDD folks, right? So how will you test this function? We haven't even written it yet. So that would be the first step that you would take. Any takers for how you would start testing this function? You don't know how it's written. You don't know how it's going to be written. It's not yet written. Any volunteers?
I give a name and I expect some prefix.
Sorry?
I
Yeah, just give a name and expect some prefix. So what kinds of tests?
like sorry, okay.
What kinds of names would you give?
Then my name.
Okay.
Some names like a predefined set of names that I have, right? And I know some set of values and I just okay, this is a guy, I expect Mr. This is a girl, I expect Miss.
Right. So you have a series of names and then expected with the I know for sure this refers to a guy and this for sure this refers to a girl. So I mean, for the purpose of our discussion, we just assume to be Indian names, or it just gets too complicated. Before we actually get to the testing part, there were lots of questions for us to ask. And I'm just going to list some of them. This, as I mentioned, are male and female, the only two categories to consider, right? This is actually very important in today's particular context because it's like a general, when we're looking at systems that learn from data particularly, we don't, and we're not paying attention to what kind of data we are throwing at them. What actually happens as a consequence of that is that the systems end up picking up all the biases that the data contains. So, for example, if you profile people in the software industry, and it so happens that the vast majority of them happen to be male, then what will end up happening in the system is that most of the male preferences will start getting captured. And you have to make a call about whether that is the right thing to do or not. So you have to start thinking about this extremely early. So it's never too late to start thinking about the social level issues when you're dealing with data. So then how do you get a decent list of names? Like why do you go and collect all of the data from? Right? I mean, you can come up with maybe 20, 30, after that you get exhausted, right? So you have to go and search. So you have to have a method for going and finding this particular name, the set of names that you want to use for testing your function. So, and you don't want to restrict it to what you can come up with or what your friends can come up with at a particular time. You want to be able to capture as wide variety of names as possible. So crawling is one particular option. These are all things that you generally look at. Today, what you can do is many people have actually gone ahead and built such data sets. So you can go Google for this kind of data set and get this, which is what I did. So, what anomalies exist in the set that I need to know about? I mean, what name? I may come across a particular name. I may not know that this is actually a name of a person. Even how am I supposed to detect that? Is an apostrophe all right as part of a name or not? Should the period be included in the name or not? What if the name has some kind of a coded middle name to it? There are all sorts of crazy things that start creeping in when you start doing crawling for even something very simple as a name. Yeah. So I need to start paying attention to what those kind of anomalies are there to consider. So, and also, if we are sourcing data from some particular party just to speed up our work, then we also have to ask this question about what do we know about the quality of the data. If the data is declaring that this is the name of a guy, like, how sure I am that it is actually the name of a guy? It should not be up to me to be the final judge of that. There has to be some way of validating it. And then with some kind of assurance. I mean, maybe the person who collected the data set gives some kind of a guarantee. Okay, maybe the 5% of the cases have errors, but probably not more. And I've done some kind of validation, random validation on this. So you have to look at data quality issues as well. So why look at data quality issues? Because you want to trust your tests. You're writing a test because you want to trust your software that you're writing. But if you can't trust your tests, there's really nothing that you can trust at the end of the day. So that's the reason you need to pay attention to the data quality. So some of the names that we come across are actually like Chandra, for example. It could be a name of a guy or of a girl, and it's actually sorry. Mark. Yeah, there are many such generic Kiran, like all the many generic names like that. So it's a question of if you're looking at a particular application. That was a fun thing that my cousin did to me. But like if you're looking at an actual application where you're expected to do this kind of prefix, we need some way of figuring out how to deal with that. Yeah, what kind of a system you build here also depends a little bit on how you would want your application to behave in such a context. So here is a list of names like what you suggested. I may test a bunch of names like this, for example. Fairly straightforward. All of these cases, I know that they work. There's no ambiguity here. But These are some of the ambiguous cases. Ambiguous cases that can actually come in various for various reasons. One is simply that they are linguistically ambiguous. Other is simply because they are ambiguous because we haven't written them down properly in English. So as I said, we noted that RAMA can be Rama or Rama. We don't know. So there can be ambiguities that arise due to things like that also. So these are kinds of details that we need to dive into when we are looking at the data set. So, and what about not names? Somebody is they can basically type in anything that they want, and what should your system do with it? So that's also something that you need to pay attention to. You may not want your function to be complicated enough to deal with all the possible words that people can type in. As long as it does something reasonable with them, including randomly classifying them as male or female, that's probably okay for the most part. So that's an application specific thing again. So actually, I don't want to keep doing that. I just want to build all of this stuff into a table as I suggested. And look up this table, and I'm going to check whether this name, what it corresponds to, and then I will just check whether the function is producing that particular channel. So that's what I want to do. And then I can give that table off to anybody who wants to augment that table as time goes by, and the test actually gains more and more strength as time passes on. So that brings to this. We have sort of completed that first cycle of building a particular table of names and gender, corresponding gender, and we know how to test our function to some extent. And one thing to note here is that these kinds of functions are actually very common in the ML world. You don't have hard test constraints, as in, if my test fails, I don't ship. That's not the kind of test that you usually run. What normally happens is that I set as a kind of a threshold of performance. I mean, I must get 80% of the cases right. I must get 90% of the cases right. Usually it's statistical in nature. So they are soft cases generally. So for if you want to write, so the test that you have written here is not kind of a very hard test. Like one fail and no ship. So now that we have such a test suite at hand, we go ahead and do our first take at the function. Right? So this is the time that we put on like our capes and go for not machine learning but table lookup. So what the easiest thing to do for the first iteration is that you just like created a whole very interesting table of names and genders. All I have to do is to look up that table and answer it. So what might be wrong with that kind of an approach? Any takers? Performance could be one.
The name might not be there.
Right.
The name might not be there. The coverage will be.
That's fine. Name might not be there in the table, so we have to deal with that in some level. Anything else? Sorry? The space the table will take. Excellent point. So it's bad for a whole number of reasons, not merely. So first thing of all is the test will never break. You don't want to have a test suite that never breaks, especially one that is supposed to be soft. Your test needs to be decoupled from your code, from your actual code. Because we're writing the code independent of the test, and we are writing the tests without having an idea of how the code is being implemented. This kind of a coupling is actually bad from day one for that very reason. And all the other reasons that you actually shared as well. So we have to ship the table. Suppose you want to do this stuff in the browser, you have to ship, and you have 120,000 names in your table, you have to ship that 120,000 names. It's not feasible. As you mentioned, it doesn't work for names in the table, so you have to make a special consideration for that. But at the end of the day, we can actually do better than that, because we actually do better than that. Every time somebody comes and like tells you a particular name, you don't actually go and scan the internet for whether this person is male or female. You have an intuition about whether the name actually stands for male or female, right? So you certainly know something about the structure of names that you are able to tell that the gender. You sort of take a good guess at the gender from the name itself. So we should certainly be able to do better than that. So what we have just done by looking at the table is a problem that's known in machine learning as overfitting. So every field comes up with its own vocabulary, but overfitting essentially refers to the problem that you raised, which is that if I mean the best way to express it is like this: we are learning by rote, and we only answer textbook questions. Okay. That's not a great way of building a learning system. Right? If you go through school and you can only answer textbook questions, nobody will really agree that you learned anything at school. Though we've been stressed that for a long time at school as well. So basically the key fact here is that understanding implies compression of some sort. So you have to take. It's not possible for us to know every little detail and before we make a particular statement about anything. Right? So understanding involves compression. It involves. There's actually a saying that relates maps to the territory that the map refers to. So if you have a map of Chennai, and the map of Chennai is not Chennai, right? It's only a map of Chennai. And therefore it necessarily avoids a lot of details that you actually find on the streets of Chennai, including where the dustbins are, you won't find on the map. Some of the shops won't be there on the map, you won't know what names are, what color day, what day it is. There are lots of incredible minute details that are completely missing from the map, and for good reason, because we're not interested in most of that. We want to use the map for a certain purpose, that's why the map exists. The advantage of such a map is that you can fold it and put it in your pocket. You can't fold Chennai and put it in your pocket, right? So that's the purpose of any kind of understanding effort that we have to undergo. So any machine learning project, typically when you're building a particular model or whatever people are talking about as models, the purpose is to compress a vast body of information and just distill out those few things that are relevant to the problem that we are trying to solve. So it's necessarily lossy compression. If you don't throw away any piece of information there, well, you can think of it roughly like GZIP. So GZIP is lossless, PNGs are lossless, JPEG is lossy. If you look at PNG versus JPEG, you'll find that JPEG files can actually be far smaller than PNG files if you start reducing the quality of them. But still, you can get some amount of idea about what image it is the JPEG file actually stores at a far lower level of granularity. But the kind of compression we're looking at here is far more extreme than that, because it's almost logarithmic compression is what we want. Because if you have a billion data points, you don't want to store something that's just proportional to the billion data points. You want to store just 10 or 15 and be done with it, something that captures it very succinctly. So one way to actually force this constraint in this whole TDD process is to say that my function cannot use more than so much memory. Once you force that particular restraint, the person who is writing the function now has to know, okay, I can't ship this table. Okay, so shipping the table is the easiest option, and that's now out of, I have to do something better than that. And what do I do? You have to start thinking a bit more, and you have to throw more understanding. So what you gain from that particular process is that you gain generalizability. So this is one other important trait of any kind of machine learning model. So you don't want, as I said, like, we don't want to only be able to answer textbook questions. No, we want to be able to answer, say something about the questions that are coming that are not necessarily in the test set that you have. So you have to have digested some information about the test set that you're working with. So this is our typical pair programming setup in TDD. There's one person who, at a particular point in time, not always, like one person takes on the responsibility of testing, and the other person takes on the responsibility of coding the test. This is actually very ideal in many ways for a machine learning project, because there's lots of mental patterns that can start interfering with this whole process of model building. So people who are not generally very acutely aware of some of these mental habits that don't work very well in this kind of a scenario, there's a certain kind of a protocol that's been developed in the ML community that is followed, which I can describe now, which is very similar to what happens in pair programming itself in extreme programming. So what the tester does is, tester is the one who prepares this big table of names and gender pairs, and what the tester does is he or she gives the 80% of the table content to person is going to code it up. The 20% is just kept secret. The coder cannot even look at it. So, and whatever the coder is producing, uh,
Check the back.
so the 20% coder cannot actually see. It's just a distance problem to the radio file. So we were talking about the secret test set, right? So when so this person just hides that particular part. So the coder has no clue, and it must work in the blind and produce something that will succeed on that test set to the extent that the tester expects. Like maybe you say, okay, you got to be correct 80% of the time, or whatever figure the tester sets. I mean, that's only part of the story here. This is not it's not the entire story. So, what a diligent coder would do is not make use of that entire table and 80% of the table that's handed over to her. And so, there are ways of dealing with, ways of getting more out of the information that's given to you because you want to iterate on your code. So you don't want to first take a look, okay, I've got this, say 50,000 names here, let me go read all of them. Okay. And then I'll figure out something about a code and I'll write a function and then give it to the tester. Life doesn't work like that because your first take on your function is likely to be wrong. And you want a method within which you can iterate on whatever function that you're writing. So you have to have your own methodology inside to work with the data that's been given to you so that you can succeed on that secret test set that the tester has. So what you can do for that is to split your own thing into what's called a dev set and a training set. While the training set is something that you go through and you read for patterns or you try to understand what's going on there. And then test your hypothesis about whatever you have understood there on the dev set. So that particular split is something that's completely up to you. You can do that at random. You can split 80-20, split it 90-10. However you want, you can do it. There are many ways to do it, many circumstances which call for many different approaches also. Not only can you do it, but you're also free to do this more than once. Now, I can do one split of dev and training, and then I'm not happy with the way my function did, so I want to do this again. What I can do is, I can make one more random shuffle of this and pick a different training and different dev set and see if I've missed out anything of this. So I can keep iterating this process until I have had an opportunity to look at most of my data, or at least most of the important parts of my data, as many times as I need to satisfy myself that I've done the best possible job here, and I can't do better. So once I've convinced myself, if I'm the coder, once I've convinced myself that I can't do any better, what you do is the way my function is done now, and then you pass it to your tester. And what the tester would do is the tester would give you a report about how well you did on that secret test set without, use that test set mostly, but this is actually a very important part. Use the test set on this only once. Because the moment the tester tells you that you've done your code correctly predicts 85% of the time, on this particular set, that is already giving you some information about what's there in the test set. If you are allowed to iterate this whole process again, what will slowly happen is you will end up learning everything that was originally secret about that test set. So it will not be a secret to you anymore. So you cannot iterate. That secret test set is use and throw. You cannot use it again. So these are some of the mental disciplines that machine learning folks have kind of worked out in order to not go into those kinds of pitfalls as they are building models. Otherwise, what will end up happening is that they will end up doing human learning and they will end up calling it machine learning. That's that's about that. So I want to take a bit of a pause here and reflect on what we have discussed so far, because we haven't talked almost anything about the actual algorithms or math or anything like that just yet. We only talked about the data, right? Because that is normally the crux. This is a huge. I can't emphasize this. I mean, even if I say this 5 more times, I won't be. I won't have any qualms saying it 5 more times actually. So it's just about the data and how you want to make use of the data to accomplish the objective that you're looking for, that you started out with. So as I mentioned, it's usually the most expensive part of the process. So and you better get that data part right, or the rest of whatever it is that the ML experts are going to do is really going to go for a toss. So extremely important. Can't say much more. I mean, I can say much more. So now let's actually get down to how we build something that learns from that kind of a data set. Right? So, so I want to be able to express what happens in this process of learning. I mean, as a coder, I'm looking at this data and I'm doing something and I'm figuring something out. There are some patterns that come to my mind. There is something that I'm digesting about this data. So what's actually happening? What's that particular process? I want to be able to capture that process succinctly so that I can put it into a machine. That's the next step. So we've so far done human learning with the human coder. If you want to make the step to machine learning here, you want to capture that process and put it into the machine. But you need precision for it. So what we're looking at here is, I'm going to use my favorite quotation again. It's all this is saying is that what is a learner? So a learner basically takes some amount of data, and as a consequence of looking at that particular data, there is something fundamental about the learner that changes. So there is a learner that's part of the output, and as a consequence of consuming that particular data, what also happens is that the learner now gets a new capability. So the learner is now able to make some predictions about the genders of names, however wrong they be. If you're only exposed to 10 names or something like that, you may not be able to do a great job of it. But that's fine. However wrong it is, you have gained some new capability by looking at that particular data. So that's all that this statement is saying. So a learner is basically a function that takes some data and produces a learner and something that guesses genders from names. It's the output. So what is, I'll just elaborate on that. What's a guesser? We've already dealt with that before. It's a function from string to what the gender is. We already dealt with what the data is. In this case, our data is simply a table. We just have names and genders corresponding to that. And that notation simply means that this is a list of pairs of string and gender. That's all that means. And finally, gender, we just stick to male and female. So it's a very simple thing, except for those first three. If you look at what learner is, it's actually depicting a process in a functional way. Having this kind of a separation in our mind very clear is very useful. It's useful for various reasons. One is that you can look at the learner as a snapshot. I mean, this is me as a coder as I was at 10 a.m. this morning, and before I looked at this data. If I had seen a different piece of data, I would have learned something different. So you are able to now think and articulate about these different pathways that you can take depending on what data is visible to a learner at any given point in this result. So if you think about this in a mutable way, then you don't have that freedom to explore the possibility of different training schedules. Like you may decide that, for example, if I have 10,000 records and I want to pass all of them, maybe I'm not going to pass all of them at one shot. Maybe I will pass 1,000 by 1,000, look at what's happening to the learner, whether the learner is actually succeeding. Because maybe 10,000 takes a long time to execute, and I don't have all that time to spend. So if I'm going to send it 1,000 by 1,000, then it may matter which 1,000 I send first and which 1,000 I send second. So you need to be able to examine this particular process of how the data is actually fed to the learner and how the learner is evolving as the learner gets to see more and more of the data. So it's very useful to have that very explicitly in your system. And at every part of this, you're free to go and take the guesser and check how the guesser is doing on your dev set if you want to. So the one thing that we saw, one problem that you actually raised was that how do you deal with things that are not in the table? Right? How do we deal with things names that we haven't looked at before? So we know something about the phonology of names. We understand what the sounds of names are like, and something about the sounds gives us a clue that this name is female or this name is male. So in order to be able to generalize, if I always have to look at name in full, or every aspect of name, or a collection of name all the time, then it will be very difficult for me to come up with a model. So one way to increase the ability of a model to generalize is to look at less data. So how do you if you know something already about how names are structured, what you can do is you can say, okay, the names have all of these kinds of things, but I know for sure that all of these are not relevant because that's not what I'm looking at when I'm making my guess. So probably I'm not going to pay attention to that, and I'm only going to pay attention to a few things. So what you might do is that's what is called feature. So you're looking at a particular feature of your data, or you may look at one or more features, and you can extract as many of them as you want. But the purpose of that particular feature is so that you can pay attention to only some aspects of your data, and therefore reduce the amount of data that you have to consider. So one consequence of this is that the data that you look at actually shrinks a lot. And if it doesn't shrink a lot, then you don't have a very good feature definition. So it's almost, it goes both ways. And the smaller the data space, the easier it is to collect enough data. So if you have to look at entire names, and names could be 10 characters long, each character is 26 possibilities. If you want enough coverage of this space, you have to do 26 to the power of 10, which is like, you can go on Google how big that number ends up being, right? So you want to be able to reduce that space of data as much as you possibly can, so that it's manageable to deal with it. Otherwise, you simply won't have enough data. So other thing that features let you do, as I mentioned, is it lets you capture the information that you already know about it. So in this case, one possible feature is that I'm only going to look at the last two characters. So last two characters, 25, 25, roughly, there are only 625 possible combinations. I can collect enough data about this. If I collect 10,000 records, it's already 10 times per pair of this. So there's enough already. So that's one possible feature that I'm looking at. And maybe I chose two in this case, but maybe one is enough, or maybe three. I'll pick. That's up to you. How big you want to make that feature space. So, but how do we look at features within the framework of whatever we discussed so far, right? We dealt with learners, and what is a feature? In this case, I'm only looking at the last two characters, so the feature is still a string. And what's my feature data? It still looks the same, but now my feature there is only consists of two characters, and not anymore. But it still has the same table structure. So I need to be able to compute this feature from given a string. So obviously I need a function that takes a string and produces a feature. The feature could be it's not only some parts, the feature is not only part of this, it could be some kind of a summary of everything. For example, the length of the string could itself be a feature. And there's an integer feature in that case. So there are no restrictions in that front. So now my guesser takes on a different form. Now I need to only guess by looking at two characters. So that's all the function that I need to write. And my learner, therefore, also takes a different form. It takes feature data which only maps two characters to gender, best case of gender. And the learner learner F is basically, it produces a modified version of the feature learner, and then the guesser function only makes a guess based on the two characters that it sees. So now this is the transformed learner process that we are looking at, where we are looking at feature spaces that are far smaller than the full data set that we originally started working with. Now we are much better placed to actually build our model. So how do we use these features? Right? So this is now, I mean, we turned over, because we extracted these features from strings, there is a very simple way to just put it back together and get a full learner from just the feature, from the feature-based learner. And you can write it in an extremely short program. So what the second line is, what I'm saying here is that the learner basically takes a feature extractor, which is a string to gender, string to string, and a learner, and produces the full learner. So we are taking a feature learner and producing a full learner. So as I mentioned here, the learner is there, there's a feature extractor, and then the feature learner, and then the full learner actually takes the data, actual data as input. So there goes the data. So first thing that I need to do is to transform the name into only those two characters that I'm looking at. So that's as simple as that. The second thing is to apply the feature learner and make a new feature learner and gain some new capability to do some predictions. So the F prediction is the feature prediction, and the LF2 is the new feature learner that we have gained as a consequence of looking at that piece of data that's now available. And then now I make a predictor for the name by only extracting the last two characters and using my feature learner to predict the gender based on those last two characters only. Very straightforward. And that's my complete learner. So this is one of the ways you can use this kind of notation to really look at how to factorize your system into larger, I mean, we started with something very general, but then we are introducing a new idea here, and we know precisely how this idea fits into whatever it is that we are building. So this particular approach is starting from types actually very helpful to do that kind of factorization. So what I'll show you here is, I'll walk through a bit of Python code which has all the elements that I've shown thus far, so that you also have an idea of how this looks like. I mean, this is not production code because I'm not using any library that would normally be used in production machine learning, but our purpose is just to illustrate how to go about doing this. So the way we'll approach this is, all we do is we just tabulate these two characters, and we look at how many times each of every two character combination occurs for male names, and how many times each two character pair occurs for female names. We just make one small table. Because that table is much smaller and it's finite in size, it is something that we can make use of to take a guess about whether a name is male or female. So I'll just switch over. So that's, I mean, I can walk you through this. You don't worry too much about the details of it. Just if you just focus on the function names, that's quite adequate to understand. So we are looking at the first step, which is the pre-process. As in, we're talking about all these kind of odd characters coming in, dots and hyphens and ats and all those crazy things. So that first step is just to, I'm not going to worry about all of those characters. I'm just going to worry about the lowercase version of the name, and I'm going to ditch every other character. So next is, all it does is just reads a list of names from a given file, which to use as a data set. And suffixes is our feature extractor. What I labeled as using that feature extractor term. So all it's saying is that given a k is like number of characters that I want to, number of ending characters that I want to use. All it does is it picks out just those characters and leaves everything else out. Counts is again an extremely simple thing. It just takes a list of those things and counts how many times each each character pair occurs in the data set that's given. So one thing that we do here is the split. I'll come to the split a little bit later. So my model is, as I mentioned, is going to be extremely simple in this case. What if all the information that I need is for if I'm given a male, and for male names, out of all the male names that I have, yeah, how many times does a particular character pair occur? And that's the only information that I need. And likewise for female. So this is a typical, very simplistic statistical model where we're modeling what's called a joint probability distribution of that. But I mean, complicated term, but the only thing, all it means is that you're just counting samples at the end of the day. And the data set is, again, very simple. I'm just reading the male names and the female names from a particular file and taking a copy of it. So the so title is what I was calling guesser. So title is the Mr. or Miss that I want to add to the name. So it takes the model that I have and it takes a name and gives a guess about whether that name should be prefixed with a Mr. or a Miss. As simple as that. And to do that model, what it does is it looks at how likely is it that if this thing is a name, then the last two characters are indicative of that this is a male. And likewise, it checks whether, given that the last two characters are what I'm seeing here, how likely is it that it's female. Okay. So, and if the M score is more than the F score, it says, okay, this is male. Otherwise, it's a miss in front of it. Very simple to read that in this case. So for training, all I'm doing is I'm just applying my feature extractor and counting and creating my models. So evaluate is an interesting beast here. So one of the things that you need to do when you're looking at machine learning models is evaluation is actually a pretty hard problem in general. There are many metrics that you'll come across for which are useful in various reasons and they have their own positives and negatives, and there is considerable amount of material to learn about that. Mostly though, the starting point for all of this is what's normally known as a confusion matrix. As in, we are looking at guessing males, whether the name stands for male or female, right? So if the name is male, we may guess that correctly, or we may guess incorrectly. If the name is female, we may guess correctly, or we may guess incorrectly. So there are actually 4 different possible outcomes for what we are looking at. So the main evaluation for my model has to come on all of these. All these 4 numbers are important. I may perform differently on males and females depending on the kind of data that I'm seeing. I need to know how well I'm doing across a particular training set. So I was actually planning to show you a little bit about how that works. Let me see if so I'm just going to load that particular Python file and just going to show, just give you a feel for what it is like to test things. So let's just see. So I just want to import my model. Model. Sorry. Why not like it? So now I'm going to make a model. Let's say look at the last 2 characters. So this look at the last 2 characters. And I'm not training my model or anything, it's just the plain thing there. For example, if I look at counts, we will have nothing. Right? So now I also want to load my data set. So I'll load my data set. So what I now want to do is I want to split. We were talking about the splitting between training and the test set. So I only want my model training to look at some parts of the data, and then I want to be able to test whether this model works on the other part. So what I'll do is I'll do a data set training and data set test set, and I will do a split. I'm going to do a 75% split. So the TSTR is the training set, and the TSDS is the test set. Now what I'm going to do is I'm going to train my model on the training set. So that trains my model. Now if I look at main counts, you will find a whole bunch of these pairs of words and counts of multipliers and numbers in the main table. So now that this model is trained, I can ask for a title of this and Srikumar. Let's see. Like it says Mr. And if you pull a just add an I here, for example, it says Miss. So it's doing something, right? But I want to have a better idea of what whether it's actually working or not. It looks like it's working. Next time, it will fail here. Let's see. Let's try our ambiguous cases. Let's see what we get from Chennai. Like we put a choice. So we want to be able to evaluate this. So I'm going to evaluate the model, and I want to be able to evaluate your. So the model and the classifier, which is the title in this case, and what are all the collections and tables. I'm going to walk, and basically the evaluator walks through all possible combinations of the collections of the tables and calculates how it performs on each of these. So it actually finds out what about where all are being wrong in the main cases, where all are being wrong in the main cases, where all are being right in the main cases as well. So that's what I need to do. So the classifier is title, and what I'm so and what I'll do is now I have to use my test set, right? So I'll use my test set, names, names. That's an array of two, and then I want to tabulate against both my possible releases. So you see, it's without four numbers. So the first number here, this male names against Mr., which means I've got 77% correct. Whenever the name is a male, when the test set 75% is correct, 22% is wrong. And in the female case, in 13 odd percent of the cases, I got it wrong, and 86% have actually succeeded. So now all those four numbers are actually important because as the number of categories increases, the ways in which this thing can get mixed up is actually getting more and more complicated and very interesting. There are ways of dealing with that. So that gives you a flavor of how these kind of models work, and it's not something that you really need to learn from later things in order to implement. It's something you can build very simply. Now that code is completely self-contained. You don't need anything beyond the regular modules or so so what I showed here is how we are time. Yeah. So what I showed here is an extremely simple model. It's called a generative model. So it's modeling modeling all the cases where two character names and the thing the predictions are coming together. There's another kind of model called discriminative models, which is actually very interesting because most of the state-of-the-art models that you get talked about in the news regarding machine learning and AI, they end up being discriminatory models. Discriminative models. The we need to know something of the, it's actually a very interesting process to look at also. The process is very simple in this case. The goal is, we want to be, how do we learn? I mean, it's actually somewhat mimics the process of how we ourselves learn. You try something, okay? Then you look at, yeah, then you look at whether you like your outcome. And based on what you are seeing there, you can make some changes to what you have tried and then try again. You can keep doing this, and as long as you're making improvements, you'll be happy. At some point, you will stop. Okay? If you're happy and say, okay, this is, I don't need to do anything more than this, and I can stop here, you can just stop this whole process. This is a very simple learning cycle that we have to go through. You don't do it this systematically ourselves. Sometimes we get frustrated, all of that comes in, but that's all different issue. But overall, this kind of a method generally works. And basically, the distributive models exploit this kind of a structure in the learning problem. So now we are looking at learner as a kind of process that produces learner. Right now we kind of split it out a little bit more. We're going to do something a little bit more specific. So I want to look at my learner as having a bunch of knobs to it. It's a machine that makes some predictions about whatever it is that I want it to make predictions about. It's got a bunch of knobs that I can tweak. And I have some way of telling whether the knob setting that I have is working for me or not. That's what the error function tells me. It says if I run this machine on this whole bunch of data that I want to test it on, it gives me a number that tells me clearly whether I'm doing well or not. If the number goes down, then it is going down and I'm doing better. If it goes up, I'm doing worse. So I have some metric by which I can understand whether my knob setting is good. And the update function is the interesting piece here. The update function is telling me how to go about tweaking my knobs in order to make the error less. Okay. That's a pretty complicated thing because normally the error number is a single number at the end of the day. If I have 10 knobs, which knob do I tweak next in order to make that single number change? I mean, there has to be some particular pattern to that. And the update function captures enough information about this whole machine that it's able to tell you around this particular point, your current setting, it's good to turn the first knob by 3 notches, the second knob move up by 5 notches. It gives you an estimate of what will actually work well. And a whole slew of algorithms are actually designed around telling you how to do that particular update process. So if we don't pay that much attention to the actual algorithms themselves, but that's the core idea behind it. And that's a very easy idea to understand. So what my error function is I'm just taking a bunch of data, and I know all the knob settings for my model, and I can calculate an error out of it, right? And the second one is the update function. Given an error, and given where I am right now, it's going to be able to tell me where next to go and try. I may succeed at reducing the error, I may not, but that's different issue, but it's giving you some idea of how to move it. And there are good algorithms that make very good guesses at that. Normally, for most of these processes, you cannot make very drastic jumps. You only make teeny little bit tweaks, but you do many of them over lots of data, and eventually with the hope that you can arrive at some particular process. So there's also a training schedule involved in it, and there is also some amount of empirical knowledge that people have collected around how to design their own training schedules. The idea essentially lies between these three descriptions that you. Okay. So that's the learning cycle. So one is so the discriminatory models basically go work with how to go the learning cycle, and that's sort of where I want to kind of launch off into some bit of what is cutting edge tech today. Right? So I mean, if you look at a particular process that you have built that takes lots of these kinds of knobs and produces a single function, you need to be able to figure that update function out, because the update function is like one way I can always calculate. The other way is a harder problem because you're going from n knobs to a single number. So by tweaking one number, I cannot get all the knobs to adjust themselves automatically. So it's a very hard problem. So, but if my machine is made in such a way that there is some amount of cross predictability that is established, that in the neighborhood of wherever my knobs are, if and I'm able to figure out how to go one way and the other, then I can do something interesting here. I can predict, and I can use that same knowledge to go and learn again. So I don't have to necessarily hand code my own update function separately. That's what this whole idea of differentiable programming is about. Normally, when we are writing programs, we just rewrite functions or methods or however we structure our code. It takes a bunch of arguments, it spits out a bunch of arguments, it brings out some statements. But we don't generally ask the question of what happens in the neighborhood of a particular value. If I supply a slightly different value, what happens? Or what should the input be in order for the output to be this? Those are the kinds of questions that we don't normally ask. But those are the kinds of questions that are very important for learning systems. You want to be able to figure out the other way, actually. You know how to go one way. Like you want to be able to figure out the other way. If you're looking at some of the larger, more famous situations, the cat versus dog classifier, for example, right? The cat image and the cat label are known, and I can tell you this network, but unless I have a way of figuring out how to go from what the network is telling me versus what the cat label is, and unless I have a way of figuring out how to tweak all of these knobs in order to make this a better predictor of whether it's a cat or a dog, it's a non-starter problem. So, deep learning got really famous, and there's some amount of talk about whether differentiable programming is essentially a rebranding of deep learning, and it's maybe one more hype phrase that's going to come about. But we don't really know that at this particular point. I personally think there is something of a fundamental shift that's happening in the way machine learning models are getting built because of this as a generic capability. The evidence for that belief is coming from two languages in particular, Swift and Julia. So there are teams that are working on both Swift and Julia, which are building this differentiable programming capability as what's actually referred to as automatic differentiation capability right at the language level. So you don't have to implement it yourself. So when you write a particular function or a series of functions, you can write fairly complex functions, especially in the Julia in particular. You can write recursive functions, and you can write branches and all of it, and it manages to figure out how to do the update, how to calculate the update function automatically. That's a huge boost to the general creativity, because writing that update function has been a big bottleneck so far. And it's easier for people to write the error function than the update function. So that's the thing behind differentiable programming. If you are still game, and what I can do is I can give you a little bit of a taste of what it is like by just looking at functions of single variables. Let me see. So, I mean, again, I'm just going to sketch the idea behind this. This is, and I'll show you how this works. But this is less than 50 lines of code, and it already does it for the vast majority of math functions that we normally use. And the thing is that the core of this particular idea with respect to one variable is extremely simple. But the general production machine learning models don't deal with one or two or even 10 variables, they deal with millions of variables. And that's where the general compute costs come from. The number of knobs that you need to tweak is actually extremely high. In many cases, there are hundreds of millions for very large models. So, what the lines 3 and 4 is just the core idea is basically there only in lines 3 and 4. Everything else is almost automatic fallout of just that particular decision there. We know normal functions like sine, cos, exponential, we know all of those functions, how they work. We also know how to differentiate them. For example, if we take the e power x function, I know that if I differentiate it, I get the same function, e power x. So some of these rules I know about differentiation. What that particular line 4 is capturing is that it captures this notion of a function and its derivative simultaneously. So that when you're making any calculations with a particular function, it simultaneously works out what its derivative is going to be in every single step, in lockstep. So, so the first part of it, which just says it's a function of x to x. X can be float, so it's a floating point number. It says it's a function takes a floating point number and produces a floating point number, which is like exp or sine or cos or anything. The second part of this is interesting because this is referring to this. So it's saying that the derivative of a function is itself a differentiable function, which means I should be able to calculate as many derivatives of a function as I need for the problem at hand. So that's an important recursive step, and it's not, and the reason it is actually so simple here in this particular case is for a particular language feature. You will have to do a little bit more work to implement it in other languages like maybe JavaScript or Python or anything. I mean, this 15 lines of code, if I were to write it in Python, it will probably be 200 or 250 quite easily. Possibly I haven't written it, but like I think so at least. So these two are simply accessors. All they are saying is they access the first part of it. DF accesses the second part. This is just for convenience, so you can ignore them. And here's how we are defining the nth derivative of a function recursively. We haven't defined any functions, and we are already able to start defining the nth derivative of a function before we have actually having defined any particular function. So that's actually very interesting just by that recursive definition there. So it says the zeroth derivative of a function is the identity function, and the nth derivative is basically n minus 1th derivative of the first derivative. That's all it says. Very straightforward ideas there. And identity function is a very simple one. It's the first part of the identity function, and the derivative of the identity function is 1. We all know that. So that's a straightforward constant. So now the rest of this code, all this is about, is simply expressing all the rules that we know about derivatives. So it just says that if you add two functions, then the derivative will also add that. Then when you multiply two functions, you have to apply the multiplication rule. So you have a times derivative of b plus derivative of a times b. That's all. So all of them are basically just listing out all the mathematical rules that we have learned about in calculus and high school. That's all it's doing. Nothing more. Okay. So in the second case, it's doing the same thing for reciprocal, 1 over function there. And in these cases, it's just calculating it for all the scientific functions. So if you look at sine, for example, it says the derivative of sine is, because a itself can be a function, you also have to consider its derivative. So it says cos of that function times the derivative. And likewise, derivative of cos is basically minus sine times this derivative. It's basically all of those that you already know. Nothing fantastic that beyond all of that. Now we get some very interesting ability that we don't normally see. So let's see how this works. So I'm going to load up the library. So here I can ask for the type of x. For example, it says x is a differentiable function of real numbers. Okay. So if I want to calculate the value of x at 4, something like that, that's how I calculate it. If I want to calculate the value of the derivative of x at 4, calculate it like that. It says it's 1. So I know I'm able to differentiate x, and that's a big deal. Okay, so now if I want to calculate the second derivative of that, it says it's 0. That sort of figures, right? I mean, nothing fantastic about it. Let me do something more complicated. Now I'm going to define the square function. Okay. So this is a square function. I want to calculate the square at, do the same 4. What you get is 16, straightforward. So now I do the first derivative of square at 4.0. That's 2x. So x square, if you differentiate, you get 2x. So you're getting 8 there. And if I calculate the second derivative of it, I get 2. So one more, 2x, if you differentiate once more, you get 2. And that is independent of what value I put. You will get 2 no matter what value I put there. If you differentiate it once more, I'm going to get 0. Because the constant of that function. So whatever expressions that you know right with x, sine, cos, exp, everything, you can calculate as many derivatives automatically as you want in this case. Now imagine this at a scale of 100,000 or a few million variables. That's what we are talking about when we are looking at production scale differential programming. systems or deep learning systems. In other words, they're sort of like mixed at this point. Looking at tools like PyTorch, for example, it's largely used for deep learning work and also has automatic inferencing. So this is a kind of a baby step into this world that's coming up. It's a very interesting times for them. So we get back to this. So that sort of brings me to the closure of this. I just want to summarize some broad takeaways. One is it's all about the data. Bad data gives you bad models. So you need to spend a lot of attention on data. Do not skip it because there's always this kind of aura attached to working with ML algorithms and neural networks and all of that. You ask any graduate coming out of college these days, what do you want to work on? It's like, I want to work on AI. Like, oh, what the hell is AI? Right? So, but nobody wants to work on data. But that's the real clincher there, because it's very important. So your data, training plan, tests and metrics must come first. Because if you don't know what your system is expected to do and how you will measure that your system is expected to, the system will actually do that, you cannot even start building models that will actually do that. So this is your very first step. And this is nothing more different from the regular TDD approach that we follow. Who follows TDD approach? So,
we should follow this.
yeah, we should follow. Who thinks we shouldn't follow TDD? Anyway, there's lots of discussion that keeps continuing on. It's sort of also become a kind of a religion by itself. I'm not in favor of TDD as a religion in that sense, but I do think that some of the principles behind it are extremely valuable and they're there for good reason. And in this case, it really stands out that this is how you should actually approach this problem, or you'll fail. Like it's outright failure. And another important factor that we're going to need to take care of is ethics issues when we're dealing with the data. So, are we actually legitimate in making use of this information that's there in data for building model? Should, for example, gender be a parameter in our model, or should this be gender? Should race or color be a parameter in our model? It may be that our model will perform supremely well if I include a person's color, for example, right? There may be a very strong correlation, but should I do that? It's non-technical, ethical question that we have to ask ourselves. So those are all also the issues that we start thinking about very early on before model building. Because once you build a model and deploy it, you cannot erase that information from the model. Or it's very hard. So features, I just presented a very simple feature extractor in this case, but features in general are kind of the API mediating between models. So there are various kinds of models built for all sorts of purposes that do various things. But how do we actually build larger systems using all of these? We can sort of tie them all together using features. Especially what are referred to as embeddings or vector space embeddings. Of late, one thing that's happened is that how many have heard of word-to-vec, perhaps? Word-to-vec? Yeah. So what word-to-vec does is that it takes a word and it gives you a representation of this word as a point in a 100-dimensional space. And you can do some really funky things with this 100-dimensional space point. So you can do something like let's say king minus France plus what is it? King minus male plus female. You will get roughly equal to queen. You can do that kind of an algebra in that vector space. So these embeddings embeddings can actually be calculated without supervised labeled data. And that's a very interesting aspect of it, because once you have this kind of meaningful space in which you can look at your data items, now you can start you can start using that as a bridge point for all of your building more and more complex systems. And your systems that you build also end up getting more reusable as a consequence of that. So the features, and especially the vector space embeddings are worth paying a lot of attention. So, function factorization, the kind of way I did here, is a useful way to understand any system that you're looking at here. At the end of the day, machine learning systems are not actually very complicated at the structural level. It's only the implementation details that get really complicated because you're looking at, you want to squeeze out every little ounce of performance that you want, that you can get out of your machines, because there's so much of compute demand on these systems. But apart from that, the top level ideas are fairly simple. Having this notation tool on your hand actually lets you go and be creative with what kind of problems that you apply these tools to as well. And you don't necessarily have to train all your machine learning models yourself. You can leverage models that other people have built and build very interesting things out of it. And it's not out of the scope of non-ML developers to be able to do that in the near future. So automatic differentiation is helping ML adoption at this particular point, so it's worth paying attention to. That's my take on it as an opinion. The reason I say that again is that it takes away this burden of having to figure out how to write that update function. And that's a really big deal because writing error functions takes only as much mathematical ingenuity as probably 12th standard level, not much more really. Okay. So if you can, and if you have some amount of fluency with that kind of math, then you're able to express what you want in terms of a cost function, and the system can actually figure out how to do the rest for you. But you must, I mean, finally the creativity comes in how you express your cost function. So, yeah, just finished. So this is, to finish off that story, here's how my cousin did it 30 years ago. He wrote this: if it ends with A, then female. If it ends with I, it's female, else male. And he actually did a pretty good job of it. So, thanks, and that leads me to question.
Thank you so much, Sri, for giving an introduction to machine learning through a beautiful example. Thank you all for being here. You guys made it a success. Thank you.